and thank you everyone for coming to the defense. It's really great to see everyone. So the motivation for the work that I'm going to be talking about today starts with the observation that over the past few decades, we've been asking our computers to solve tasks that are more and more probabilistic in nature. So if we go back 40 years to the 80s, a lot of what we were asking our computers to do were sort of well-defined tasks with logical specifications. You know, if I make a database query, there's a correct answer to that, and I can prove that my program actually gives me that correct answer. And there are some exceptions to this. Numerical weather prediction dates back to the 50s. The Apollo lunar missions used Kalman filters to estimate, to do state estimation of the spacecraft's position over time. But in the past few decades, probabilistic computation has become a lot more widespread. So by the early 2000s, when I was learning to program, we were routinely asking computers to draw inferences from imperfect data, like inferring whether a web page was trustworthy based on who else was linking to it from the web, or inferring the words that someone said from audio of their speech. And we also ask computers to make all sorts of predictions, right, about what movies a user might like based on what they've watched before, or what words they'd probably type next. And since the 2000s, the scale and complexity of the probabilistic tasks that we're asking our computers to solve has really exploded, right? We're now building autonomous cars that we want to infer the geometry of the 3D scene around them from image data and other sensor data. We're building AI doctors that aim to infer diagnoses from your symptoms and predict treatments. And given this shift in what we expect our software to do, we might expect the rise of new engineering methodologies and tools to help us actually build software that can deliver these capabilities. And to some extent, that's what we've seen. So in the past 10 years, we've seen the rise of these really great tensor computation frameworks that compile really fast code for highly parallel devices and automate operations like gradients that are necessary for training deep learning models. But in a sense, these tools are still surprisingly low level, because the tasks that users are trying to perform are probabilistic in nature. And if you actually go read the papers that are developing the methods that we actually use to solve these tasks, they're full of equations about probability distributions. But you'd be hard-pressed to actually find those probability distributions in the code. All of the probabilistic thinking is happening in paper, and then you go implement the math that you've derived. By contrast, I'm going to be telling you about an emerging class of programming languages and libraries that really treat probability distributions and probabilistic operations as first-class citizens. And probabilistic programming is a really broad field, and these various languages differ in their goals. Some of them are aimed at more specialized kinds of probabilistic computation, like the statistical analyses that people in the social sciences might do. But this talk is going to focus on some general purpose tools for probabilistic computation that my collaborators and I have built over the course of this PhD, as well as a couple examples of applied systems for solving particular inference and prediction tasks, which would have been difficult to build without the probabilistic programming tools I'm going to tell you about. And over the course of this talk, I'm going to be making an argument that we need languages that treat probability distributions as first-class objects, not only to make it easier to sort of implement and scale the techniques that people are already using in AI and other fields, but also to potentially open up a whole new class of approaches, which I'll give some brief examples of toward the end of the talk. Okay, so let me start with part one, which is about the approach that I've taken in my research to thinking about what these probabilistic languages should look like and how we can implement them. So the first key observation I want to make is that all of the most fundamental and widely used algorithms for probabilistic inference and learning rely on certain mathematical operations from probability theory and calculus in order to make key decisions during their execution. And so maybe one way to provide better high-level tooling for people who are trying to implement probabilistic computation is to find ways to better automate these core operations. And one reason to believe this hypothesis is that it's actually been validated already for one of these cases. So in the case of gradient descent, we actually do already have great tools for implementing this in a really good way. So what do I mean by that? Recall that gradient descent on paper is a really simple algorithm, okay? We write down a loss function that says how well our model fits our data for certain values of some parameters. And then we do this three-line algorithm of repeatedly stepping our parameters in the direction of steepest descent of the loss based on the computation of the gradient. But for a long time in machine learning, implementing gradient descent was not as simple as this picture makes it seem. And that's because the gradient operation needed to be done on pen and paper before going and implementing the math that you had worked out. So if you actually look at papers from the early days of machine learning, like this Schmidt-Hubert paper that introduced a kind of neural sequence model called an LSTM, it has pages and pages and pages of derivations of the gradient, ending with the lines, all we need to implement for the backward pass are equations 19, 20, 21, 22, 23, 25, 26, 27, and 28. And you sort of feel for the graduate student that had to go implement those. Especially because if the model didn't work, there was this question. Is the model bad? Did I make a mistake somewhere in my math? Is the math okay, but I made a mistake while implementing the math? Right? And that's a really hard debugging question to answer because you're just trying to see whether you're performing some prediction task well or not. And, you know, even though that math was all stuff that maybe we've all learned how to do in calculus class in high school, it's still really tedious to do for models of the size that people are working with. But this is no longer the experience of building deep learning models, right? And implementing gradient descent. And that's thanks to an innovation called automatic differentiation, or autodiff. And the key idea in autodiff is that if you've written a program to compute your loss, you've actually done more than written a program. You've actually given a completely unambiguous formal definition of the mathematical loss function that you're trying to do gradient descent on. That is, your program is a faithful representation of your loss function. And that means that the computer could, in principle, figure out the gradient of the loss function for you by reading and manipulating the program you wrote. And that's what automatic differentiation does. It's a meta program, a program whose input is another program. And the output of automatic differentiation is a program that faithfully implements the mathematical derivative that you could have derived much more tediously by hand. And it's not an exaggeration to say that automatic differentiation, which is a part of all of today's toolkits for deep learning, has transformed the practice of machine learning. Or at least it's transformed the practice of optimizing neural models by gradient descent. But as we saw before, there are a lot of algorithms for inference and learning beyond gradient descent, hugely important algorithms that have each birthed entire subfields of computational science. And these algorithms don't just rely on gradients of functions, they rely on a broader set of operations on both functions and probability distributions. And that's what motivates the sort of key question of this talk, which is, can we generalize and extend automatic differentiation to support a much broader family of probabilistic computations? And a very useful idea on the way to that goal, maybe the central idea in probabilistic programming as a field, is that programs can be used not just to represent functions, but also to represent probability distributions. So what does that mean? Well, when we write a program that makes random choices during its execution, we're implicitly defining a probability distribution, the same way that a program that doesn't make random choices defines a function. For example, this program flips a coin and then decides whether to return 0 or theta over 2, where theta is its argument. And implicitly, what it does is it defines a distribution on its outputs, all of its possible outputs, given its input theta, right? With probability theta, it returns 0. With probability 1 minus theta, it returns theta over 2. And it assigns probability 0 to all other possible outcomes. And if we have a sufficiently expressive programming language, we can write down a lot of interesting probability distributions in this way, including lots of classes of well-studied distributions from the machine learning and stats literatures. But of course, it's not enough just to represent distributions, right? We also want to do something with them. And this thesis is about our approach to doing that. We're going to extend the user's programming language for writing down probability distributions with 4 higher-order constructs for a handful of key operations in probability theory and calculus. So let me tell you a little bit about what these operations are. The first is the standard derivative, the one that AD already implements. Derivatives are good, we're not getting rid of that. It tells us how do small changes to a function's input change its output. The second is integrating with respect to a probability distribution, which tells us for inputs that I sample from this distribution, what is the average value that a particular function takes on those inputs. And when this distribution is a probability distribution, as opposed to a more general measure, this actually is called expected value or expectation. Okay? So I'm going to be using this symbol throughout the talk. But the tools that I'm talking about can be used more generally for integration with respect to more general measures. Now, the third operation, unbiased estimation, is kind of an inverse to that. It says if you have some number that's too hard to compute exactly, is there some distribution we could sample from that would give us cheap estimates that are right on average for estimating that number? And the fourth operation is maybe the least familiar. It comes from measure theory, and it tells us how much more likely a given outcome is under one distribution than another. And in most cases, you can basically think of it as a probability density ratio, right? A ratio of P of X over Q of x, or mu of x over nu of x. But it is defined even when the individual densities of these distributions are not defined. And that's something that has actually come up in some applications to computer vision, where we have distributions on orientations and rotations and things like that that don't necessarily have probability class 101 density functions. But basically, this is a way of getting the likelihood or the density of a particular outcome. Now, these operations are interesting in their own right, but they really shine when they're used together. So the gradient of the expected value, for example, tells us how small changes to the parameters of a distribution affect the average outcome from that distribution. And if that's too hard to compute exactly, we can ask for a stochastic estimate of it. Gradients of radon-Nikodym derivatives tell us how small changes to the parameters of a distribution affect the likelihood of a given outcome. And again, sometimes it's intractable to compute these likelihood gradients exactly, so we might ask for unbiased estimates. The expected log radon-Nikodym derivative between two distributions tells us how far apart those distributions are. It asks, on average, over samples from the first distribution, how much more likely will a typical outcome be under that distribution than under the other distribution? And this is the KL divergence from information theory. And the gradient of the KL divergence tells us how small changes to the parameters of two distributions makes them closer or further apart. And again, that's something we might have to estimate when it's intractable. So the generativity of these building blocks, letting us ask all these sorts of interesting questions, is why they show up in all of these algorithms, right? In the same way that gradients tell us which way is the fastest way downhill on the loss, these other operations can also answer all sorts of questions for other things that aren't just trying to find the bottom of a loss function, right? They can tell us, well, is that hypothesis more likely than this hypothesis? Is this a more rational explanation than that explanation? Right? And so the idea is that by giving users access to constructs within their programming language for implementing all of these operations and composing them, we can open the door to an open-ended space of computations for inference and learning that the user can navigate at will. And a key lesson of the sort of stochastic gradient descent revolution is that you don't need those estimates or those values to be computed exactly for them to be useful. So we're going to really lean into estimating intractable quantities. And the thesis that I'm defending today is a report on my efforts with a bunch of amazing collaborators over the last several years to bring this picture to life, with an approach based on modular program transformations. So to give you a better sense of what that looks like concretely, let me offer a motivating example of one place where we might need to compose some of these operations, namely the estimation of gradients of integrals. So this need arises in lots of settings, but a good class of examples to keep in mind are decision theoretic optimization problems, where we're trying to optimize the expected utility or risk of behaving in a certain way. So in these settings, there are some parameters we're trying to optimize, like the parameters that are going to control how a robot arm behaves. And we also have a stochastic simulator that, taking in those parameters, can actually simulate the robot arm and simulate a particular concrete situation. And then we have some sort of utility function that can measure how well we did in that situation. So what was the grasp error when we tried to grab this object? Did we succeed or did we miss by a certain amount? And what we're really trying to do is we're trying to find the parameters that make it so that on average, over all the possible simulations, we minimize our grasp error or we maximize our utility, right? And scenarios like this show up in all sorts of disciplines, including even the algorithms that OpenAI and other companies use to fine-tune their large language models to maximize the utility according to a human judge. But unfortunately, despite the ubiquity of these problems, there isn't a very general way of estimating the gradients of these stochastic simulators. You still have to take a case-by-case approach, relying on ideas from calculus and probability theory to come up with some way to estimate the derivatives you need. So for example, in the application of fine-tuning language models from human feedback, it's pretty simple to write down the objective that we are trying to optimize. Most papers on this are going to have it as just like one line somewhere in section 2. And what it says is like what we want to do is we want to optimize the expected value of the process that samples a string from the language model, then feeds it through a neural net that's been trained to predict what a human will think, right? And we want the gradient of that so that we can optimize it. But even though it's easy to write this down, you'll also see papers that say, here's a 12-step process that you need to follow if you actually want to get low variance estimates of the gradient. They have names like Secrets of RLHF and Language Models, Part 1. And so, in practice, it doesn't seem like the picture is as simple as the math makes it look. And what I want to do now is give you a little bit more detail on why that is. What is the fundamental blocker that makes it hard to apply our existing tools, which are great at computing derivatives, to these kinds of problems, which are ultimately derivative computation problems. And to explain what's hard about it, I'm going to look at a slightly more abstract picture of the setting that we're in, where we're going to say we have some stochastic program. It takes in inputs theta, and every time we run it, we get some value x. It could be a different value x every time we run it because it's stochastic, and I'm just plotting here samples from the program. And the thing that we're trying to optimize is the expected value of this stochastic process, right? So for any given input theta, there's some average value that the program takes on, and we plot those average values, we get this curve. Usually, we want to try to minimize or maximize this expected output. And sometimes the situation looks like this with kind of minimally noisy samples around a true curve, but the same math applies in all sorts of qualitatively different scenarios, like this one, right? This is a program that has a stochastic branch in it. So, I've given a theta, and sometimes it brings me to the high branch, and sometimes it brings me to the low branch. And it looks like the values are getting higher and higher as I move theta to the right. But if you pay close attention, you'll see that also the probability of ending up in the high branch decreases as I move theta to the right, which is why the expected value actually begins to dip if I push theta too far. So we want to optimize these blue curves. And in order to do that, we're going to try to get the derivative at some point theta, right? I'm plotting in green. But we can't get that exactly in general because we don't even know how to exactly evaluate the blue curve itself. Right? The blue curve is just some average of a process that we can sample. And so what we have to do in practice is come up with some way to estimate that derivative stochastically. And we want an estimator that is unbiased, meaning that on average, it actually equals the true derivative. And if it is unbiased, we can actually plug it into algorithms like stochastic gradient descent, which have certain guarantees when given unbiased gradient estimators. And the reason I say that we have to come up with some way of estimating the derivative is that standard autodiff tools do not solve this problem for us. So let me show you why. Here's that example we were looking at before. And now I'm actually showing the program that is used to generate these dots. And to see more clearly what's going on in the plot, I'm going to rescale the y-axis and remove the dots and remind us that we're trying to estimate the derivative of this blue curve at some input theta. Now, one thought you could have is I have this program, and it's stochastic and it's very noisy, but even though we can't compute the blue curve exactly, we can estimate it very accurately just by running my program a lot of times and averaging the results. Right? So even though it's still somewhat stochastic, the law of large numbers is going to kick in, my variance is going to go down, and I'm going to get quite close to the blue curve. Okay? And then you could say, well, I have this very low noise way of computing the blue curve. It's almost deterministic. Let's just see what happens when I run autodiff on it. And you might notice a couple things. One is that the outputs are stochastic, and that's kind of expected. Our program was stochastic. We still expect maybe our derivatives to be stochastic. But the rude surprise is that they're pointing in totally the wrong direction, right? This is not an unbiased estimator. In fact, it's almost the opposite of where you want to go. Which means that even if we can accurately approximate a function, something is going on that makes standard AD not accurately approximate its gradient. And to give you one layer more of detail on why that is, I need to give you a quick rundown of how standard AD works. And I'm going to cover the simplest version called forward mode, but the same intuition applies for reverse mode and mixed mode AD, which are used in practice. So the key idea in forward mode is the way that we're going to compute derivatives is that we're going to take a program that operates on real numbers, and we're going to replace all the real numbers that are running through that program with pairs of numbers, dual numbers, that track both a number and its derivative with respect to some external parameter theta. And for every primitive in our language, we need to implement a dual number version of that primitive that returns both the value of the primitive and its derivative with respect to theta. So for example, if we have the sine function in our language, sine of x gives me some number, we now have to implement the dual number sine function that takes in an x, but also dx d theta, and returns both sine of x and the derivative of that with respect to theta, which in this case we can compute using the chain rule from calculus class. So we do this for all the primitives in our language. And then there's actually a quite simple metaprogram, a surprisingly simple metaprogram that can take our dual number primitives and use them to give us a dual number program, a dual number version of our whole program. And it's really simple. All it does is it changes all the primitives to their dual number versions. And it changes all the constants, like 3 at the bottom there, to pairs of numbers that say 3, 0. And if you have type annotations, it changes those too. Really simple metaprogram. And if you haven't thought about it before, it's actually extremely remarkable that this yields a derivative, because derivatives are kind of annoying to compute by hand, symbolically. This is actually way simpler than the thing that you learned in calculus class. But it works. You can prove that it works. That when you start at the beginning of the program with theta comma 1 and you run it, at the end you have not only the original output of the program y, but also its derivative with respect to theta. And it doesn't just work for functions that you could have differentiated easily by hand. It works for all sorts of constructs that your high school calculus textbook didn't even have ways of expressing, right? If statements, for loops, recursion. And we had a paper last year, or a couple of years ago, that proved this correctness result in a very general setting. But if our program makes random choices, something goes wrong. So what is that? We can try to run the algorithm, but we run into an issue because we have these new primitives in our language, like flip and normal, and they're stochastic. And it's not totally clear what the dual number version of a stochastic primitive should do. Consider the flip function, for example. Its dual number version would take in a probability of heads p and a derivative of p with respect to theta, but what should it return? Should it still flip a coin? If it does flip a coin, what is the derivative of true with respect to p and with respect to theta? Where do we even put that derivative? Should it go like in some kind of dual Boolean? If it did go in some kind of dual Boolean, what would the if statement do with it? Right? And you might think that this is just some weird problem with the discrete nature of flipping a coin, but it's actually a more fundamental problem with stochasticity. Because this whole idea of dual numbers is built around the idea that we can say how small changes to inputs give you small changes to outputs. But when we make small changes to the input to a stochastic primitive, we're not changing the samples, we're changing the distribution of the samples. And so in order to implement dual number AD for stochastic things, we would need some way to cast small changes to a distribution as small changes to a sample. And that's something that you can sometimes do, and people have actually worked quite hard at applying ideas from like optimal transport theory to figuring out how to do this in special cases. But there's not a general solution to this problem, which is why the literature is full of papers where people derive special ways of estimating derivatives of expected values for particular probabilistic processes or classes of distribution. And it's also why mainstream systems for AD just throw up their hands at this problem. When you ask them to flip a coin, they just ignore the fact that the Boolean output depends somehow on P and don't track those derivatives, which is why we got these biased estimates before. Okay. So let me show you instead what it looks like to tackle this problem in our proposed language. You can think of our language as a modern functional programming language like Haskell that has higher order functions and recursion and algebraic data types, and also some primitives like flip and normal for discrete and continuous sampling. So this is a very expressive language for writing down probability distributions. But I should mention that it does still have some expressiveness limitations. In particular, in order to ensure soundness, our type system prevents you from applying non-differentiable functions to a parameter that you're trying to differentiate with respect to. And that might sound very reasonable. Why would you do something non-differentiable that you're trying to differentiate? But in the probabilistic setting, it actually can be totally okay to do that. Like uniform 0, 1 is less than theta is a totally reasonable thing. In fact, it's the exact same thing as flip of theta. But we allow flip of theta. We allow things like comparing a stochastic version of theta to 3, but we have this restriction right now on actually comparing directly to the parameter that you're differentiating. And there are some smart people who are trying to think of ways of generalizing around that, like Wanyol Lee and Sai Bangaru and Jesse Michel. Okay, but we have this generally very expressive language. And once you've written a program in that language, we're also going to let you run these higher order operations I was talking about on it. So for example, the user can define a function f that says that what it's doing is it's integrating over the randomness in the program. I can just say, my function f is the expected value of my program p. Okay. Now, note that the output type here, I've put in blue. It's not a black real number, it's a blue real number. And the reason for that is that we're using these blue real numbers to represent possibly intractable real numbers that we're not really sure that we can actually compute. Okay. So if you actually try to run f on some input, 0.6, our system is going to give you an opaque value that says there's some number here, but I can't tell you what it is, which might sound kind of useless. But the reason it's not useless is that it doesn't prevent you from continuing to apply more operations to this intractable function. So for instance, you can apply the gradient operator to one of these intractable functions and get out a new intractable function that in theory represents the gradient of your first intractable function. And that still seems maybe kind of useless, but the thing that you can do with one of these intractable real numbers is that you can ask the system to estimate it unbiasedly. And it actually is going to guarantee that it's going to give you an unbiased estimate of the thing that you said that you wanted to compute. So in this case, we actually get unbiased estimates of gradients. And we don't have to stop here because this estimator is itself a probabilistic program. So the compositionality kicks in and we can ask for the variance of the estimator, which is just the expected value of x squared under the estimator minus the true gradient squared, or we can get the gradient of the variance, or we can ask to estimate the average variance over a distribution of inputs. So this is the kind of compositional experience that we are hoping to provide to users. And in order to implement it, we came up with some new techniques for compositionally transforming probabilistic programs. So for each of these higher order operations in a user's program, we've developed a way of transforming the program they operate on into a program representing the result of the operation. So when the user asks for an expected value, we use our integration transformation. When they ask for a gradient, we use our version of autodiff. And then when they ask us to estimate, we transform the program again. And each of these transformations is backed up by theoretical guarantees that we're able to obtain by reasoning separately and modularly about the correctness of each of these transformations. But like the transformations themselves, these theorems also compose to give a proof that this final estimator really does yield unbiased estimates of the gradient of the expected value of the original program. And if you're wondering how these transformations are implemented, let me give you a whirlwind tour. So the first transformation we applied was this transformation for integration. And this transformation takes in a program that the user has written, where that program can be viewed as a recipe for taking inputs x and stochastically generating some kind of output y. Right? That's what that type x to py represents. And what they're asking for us to do with this integrate transform is transform it into the expectation operator for that program, which takes in not just an input x, but also an integrand, a function that we want the expected value of from y to the reals. And then the output of this expectation operator is itself one of these reals or vectors. Now, interestingly, this change in representation from a direct sampler to an expectation operator really closely mirrors another well-studied change in representation from the functional programming literature called continuation passing style. And the idea in functional programming is that even though the user writes down a function that takes in an x and gives you out a y, tells you directly how to compute that y, often for the purpose of implementing compilers and other kinds of analyses, it's useful to have the program in another form that takes in both an x and something called a continuation, which is a function that tells you, if you give me a y, here's what I'll do with it. And instead of just giving out a y, this program, this continuation passing program, actually says, oh, here's the final result. So if you stare at the types here, you'll see that they really look very close. And that's not just a surface level connection. If you go deep into the literature on probabilistic programming language semantics, you'll see statements like, we frame the probability monad as a submonad of the continuation monad. And what they're getting at is this connection. Practically, what it means for us is that there's this transformation that people have developed in the functional programming literature called the CPS transform that compositionally brings you from one of these representations to the other. And when we apply it to a probabilistic program, what we get out is the expectation operator. So what's actually going on here? Well, one way to understand what's happened here is just like autodiff said, I have a program that's written as a composition of primitive arithmetic operations. Now turn it into a program that's written as a composition of dual number operations using the chain rule. Here, we're going to take a program that's written as a composition of sampling operations and using the law of iterated expectation, rewrite it as a program that is a composition of expectation operator primitives. So if you look closely at the program on the right, it actually has a lot of primitives inside of it that are kind of analogs of the dual number primitives we saw before, that are things like the expected value with respect to flip, the expected value with respect to normal, okay? And that might worry you because those things are actually kind of hard to compute. We don't know how to compute the expected value with respect to normal of an arbitrary function. But that's why this returns blue real numbers. These are supposed to be intractable. And so all of these new primitives, we don't actually have to implement right now. We're just going to leave them opaque. The important thing here is that we now have a representation of the expectation operator as a compositional object, right? As a program that's defined as a composition of a bunch of primitives. And that's going to let our other transformations continue to act on this. For example, the differentiation transformation. So the program from the previous step is no longer stochastic, so we don't run into the same difficulty that we saw before. All the primitives are deterministic. And we do have to have a version of autodiff that can deal with these intractable numbers, but there's a pretty simple fix. We just do dual intractable numbers. Okay, so it's the same idea as an autodiff, but now we're going to introduce this idea of dual intractable numbers that track intractable things and their intractable derivatives. So we're going to run AD. And then we come to our final transformation for this example, unbiased estimation. And this is supposed to take our intractable program and convert it into an unbiased estimator, right? A way of sampling real numbers that actually, in expectation, give me back the number that's supposed to be represented by this intractable thing. And the way that this transformation works, actually, again, is going to look kind of like autodiff. But instead of replacing numbers with dual numbers, now we're going to replace numbers with estimators. We're going to replace intractable numbers with estimators. And we're going to do that in a compositional way. So the same way that we used to have dual number primitives in our language for things like sine and plus and times, for functions that can operate on these intractable numbers, we're going to have to provide estimator versions of those functions, which say, if you give me an estimator for my input, I can give you an estimator for my output. So for example, we have plus in our language. We're now going to have plus hat, which takes in an x hat and a y hat and says, here's how I estimate the sum using the estimators x hat and y hat. I'm just going to estimate x, estimate y, and then return the sum of the estimates. That's a valid way to do it. But a difference from AD is that it's not the only valid way to do it. There's no rule that says this is how you have to estimate sums. For example, what I could do instead is I could flip a coin and decide either to estimate x or to estimate y and just return 2 times the thing that I chose. This might seem kind of dumb, but it's actually cheaper, right? And if x and y are kind of close, maybe it doesn't matter. And on average, across lots and lots of runs, this is going to give the exact same answer. Okay. So which of these do we choose for the user? Right? Sometimes they might want to do the cheap thing. Sometimes they might want to do the expensive thing. And so we're going to have a default, but we're also going to give these names, sum and sample. And we're going to allow the user to choose these as annotations on the primitives that they write their program. Okay? And the annotations don't have to be just names. Some of the estimation operations have names that have arguments in them. In other words, the estimation strategy that you can annotate with itself might have arguments, like the rate of the Poisson distribution that you're going to sample from in this Poisson estimator of e to the x. Now, if you've ever been estimating gradients of integrals yourself and had to figure out how you're going to do it, you might know that there's this huge literature of different techniques that you can apply. And there are some nice survey papers that kind of summarize all of these techniques. And the way that this diversity of techniques shows up in our system is that these are actually different estimator rules for the expectation operator primitives and the dual number expectation operator primitives that our other transformations introduced. Okay. And this means that for the user, as they're writing their probabilistic program, they get to choose what annotation do I want to add to each of my sampling primitives. And as they choose different ones, they're going to strike different trade-offs between computational cost and variance. And ordinarily, it might have taken a lot of effort to rewrite their program to use these other estimators. Now all they need to do is change an annotation. In fact, you can wind up with some pretty interesting estimators that would have been really weird to implement by hand, just by composing some of these standard estimators. So for example, if we have a program that just flips a bunch of coins in a row, the ordinary program is going to look like I flip x1, I flip x2, I flip x3. But if I give them this MVD, measure value derivative estimator, the estimator program that I get out does this weird thing where it runs the program once, I'm showing that in gray, but it also considers all of the edit distance 1 runs of that program. What would have happened if only x1 had been different? What would have happened if only x2 had been different? And it uses all of those edit distance 1 runs in order to get a really good estimate of the derivative or the sensitivity of the output with respect to the parameters of those coin flips. And this estimator was known as the phantom estimator. You can think of these as like phantom executions that didn't run before in the operations research literature. But for us, it's not some different estimator. It just arises out of a composition of these measure value derivative estimators. Okay, so that's how things work behind the scenes. But how well do they work? So we've implemented our approach in several host languages, including a great new GPU accelerated implementation in JAX by my colleague McCoy Becker. And in addition to implementing these gradient and expected value and unbiased estimate operations, we also have this radon-Nikodym derivative thing from the intro to the talk and from chapter 4 of the thesis, which means that in theory, we could do a lot of these or all of these compositions. But the places where we've done the most empirical validation are using radon-Nikodym derivatives within Monte Carlo inference and using gradients of expected values of radon-Nikodym derivatives for variational inference, really estimates of these things. So we've implemented a handful of case studies based on modeling and inference problems from the literature, and we set out to answer a few questions. First, having our tools lets users do a kind of hyperparameter search over many possible stochastic approximations to the gradients that they need, because we can just switch out different annotations after we've written our program and look at how the estimators perform. And we wanted to know, how valuable is that? You know, are people who just go and implement the thing that they think they should implement actually losing out on performance that they could have if they tried a bunch of alternatives? Or are people basically having a good way of getting the right thing already? So for our variational inference case studies, we compared the convergence of training versus wall clock time using a bunch of automated estimators in our framework, as well as a reference implementation using Pyro, a probabilistic programming library in PyTorch. What we found was that the best estimator from our framework led to 5 to 10 times faster training than the worst estimator. And the worst estimator was the one they originally used in the paper. Right? So this suggests that actually, maybe practitioners are reaching for estimators they know how to implement, and that having tools that let them better explore that space with no additional work could really be a big win. The second question we had was, for experts who know how to write their own estimators of gradients and radon-Nikodym derivatives, what kind of overhead do these tools introduce? And this is not a fundamental question about the approach necessarily, but it's about how far we got in our implementation efforts. And we found that there is some significant overhead, especially in our Julia implementation. That's my fault. McCoy's implementation does much better. But what's interesting is that because we're using these fast unbiased estimators, when we actually plugged them into larger algorithms like MCMC or SMC, the bookkeeping that those algorithms were doing already dominated the runtime. So the actual overhead was closer to around 10%. Now, another question we had was, we're doing this unbiased estimation of these quantities. And that's really well studied in the stochastic optimization literature, but it's received a little less attention in the Monte Carlo world. There are people who thought about it, and we've even had a paper at UAI studying some of the theoretical properties of this. But now that we have these tools, we wanted to do an empirical study. So for each of our Monte Carlo case studies, we implemented 3 versions of the same algorithm. And in all the plots I'm going to be showing you, the blue curve is the algorithm that uses our system. The orange curve is one that uses hand-coded estimators, but it's the same statistical estimator as the blue curve is using. And the green curve is if we actually try to do the intractable thing of getting an exact radon-Nikodym derivative or what have you, okay? And sometimes we've had to do exact, but still approximate, like an expensive thing that didn't get all the way to the full thing. Now, the first thing we found was that maybe unsurprisingly, the cheap unbiased estimators alone can be way faster than trying to actually compute the intractable thing. That's not that surprising. We're doing a cheap thing. If I showed you that the plus that only chose one of the arguments to evaluate was faster, you'd say, well, yeah, but does it hurt you that you're using these fast things? That's the real question, right? Do we get variance that's too high that actually ruins the performance of overall inference and training? And empirically, we found that variance didn't really degrade the inference overall. This is a little bit surprising at first because, and we were surprised by it. So we also looked kind of closely at, well, what about the actual little metrics of what's happening at each iteration? For example, in Metropolis Hastings, are we accepting moves less because we're using these faster, higher variance estimator? And the answer was yes, we are accepting moves less, which then makes you think, well, how can the inference curves possibly look like that, where there's no difference in the convergence rate in terms of number of iterations? And the answer actually comes from something I learned in Josh's class, I think. This one and done idea, which is that there are a lot of decisions that algorithms like MH have to make that are quite close decisions. If you did your exact computations, you'd say, what I should do here is flip a coin. Okay? What I should do here is do 60% probability of accept, 40% probability of reject. Now, is it really worth it to spend all that effort figuring out that the numbers are 60 and 40? Or is it okay if you just throw up your hands a little bit and guess a number, and then flip a coin with that guessed probability, right? It's already noisy. Maybe you don't have to think that hard about what probability you should accept with. And the things that are really clear that you should accept, which are the big jumps in the y-axis on these algorithms, are still going to be really clear if you do a cheap estimate. And we found similar results in other algorithms like sequential Monte Carlo. Now, zooming out here, what is the upshot of this? What is the value of these composable program transformations? And one optimistic answer is that we might hope to actually see an analogy play out with the impact of standard autodiff on deep learning. So I showed you before what deep learning looked like before AD, pages of derivations. And now if you look at a paper in machine learning, it says, we computed the gradient, right? And that's because everyone knows that there are tools that are going to do this for you. You don't need to do any derivations in your appendix, and you might even get dinged for trying to pass that off as technical work. And it's interesting to actually look at the impact that this had on research activity in deep learning, because I think a lot of people rightly attribute the exponential interest in deep learning to this AlexNet moment in 2012, when a team showed that deep learning could achieve really amazing performance on image classification compared to alternatives. And I think that's right, that sparked a lot of interest. But that interest couldn't actually be translated into research activity until it became accessible enough for a large number of researchers to actually start doing that research. And so once you see tools like TensorFlow start to be introduced in 2015, you really start to see the curve take off. So one thing we might think is that in the same way that current tools for automatic differentiation have enabled rapid application and iteration with certain techniques, which have enabled the amazing capabilities of plausible generation of images and text, pattern recognition, very general function approximation, new probabilistic generalizations of AD could help to rapidly explore many new approaches to probabilistic prediction and inference, which is useful not just because some people are already trying and struggling to apply these techniques, but also because when combined with the deep learning toolkit, they could open up new ways of addressing some limitations of today's dominant machine learning systems. And so in my last 10 minutes or so, I want to show you what that might look like by giving you two really quick introductions to systems that we've built using these probabilistic programming ideas. And in particular, I'm going to tell you about one system for scalable probabilistic reasoning about relational data, and another system that Vikash mentioned, or set of systems, for integrating more symbolic computation into language models. And both of these are going to use some of these algorithms that require more than just gradients of functions in order to implement them. So the first is for reasoning about relational data. So in many domains, we have a bunch of data. And in order to reason about it clearly, as people, we need to think not just in terms of the data itself, but in terms of the real world objects that the data mentions. So we might be looking at a flat list of textual citations, but in order to reason about them, our mental model is that there's some imaginary relational database of papers and journals and authors and citations between papers. And we're just looking at a messy projection of that database. And because it's impossible to know the full relational database with certainty, given just the data we can see, reasoning about it requires some amount of probabilistic inference and prediction. And as people, that's something we do really well, right? So for instance, if we're looking at these 3 rows of a data set of apartment listings in the United States, and we're wondering whether the apartment in the first row, which is missing a state field, is in California or somewhere else, the first thing we might notice is that Beverly Hills is not a city that we've heard of. But Beverly Hills is one that we've heard of. It's a very well-known city. We might think that that's a typo, and especially when we look at the description and see that it's actually spelled Beverly Hills over there, it's like, okay, yeah, probably it's Beverly Hills. But then we have a problem because the rent per month is $1,000 for a cozy 2-bedroom in the heart of Beverly Hills. That doesn't seem possible. And it's just run by these people, Tim and Sarah Jones. Who are those people, right? And I look elsewhere in the data set, and it's not a total match on the name, but they already make some typos, so maybe that's still them, right? Tim and Sarah Jones, and then they've got a bunch of listings in St. Louis. So what's going on here? Like, at this point, I might go to the internet and type in Beverly Hills and see that there actually is a Beverly Hills, Missouri, right? And so people can, I don't know, I wouldn't necessarily bet money on this, but if you forced me to, I might say it's more likely in Beverly Hills, Missouri than Beverly Hills, California. And that's the kind of weighing of different sort of sources of evidence that can all sort of interact with each other that we were trying to get at in this project, seeing if we can automate something like that. So the system that we built works like this. The first input to pclean is a tabular data set that might be messy or incomplete. So for example, here are 4 partial rows of data from a Medicare data set, recording information about physicians and the practices where they work. And the kind of world knowledge that we're using in order to solve these tasks is encoded in a short script where the user can posit a schema for the latent relational database of objects, like medical schools and physicians, that they think might underlie the dirty data set. And that script and the table are fed into pclean. And what pclean does is it tries its best to infer the contents of this latent relational database from the flat, dirty table that the user supplied. So in this 2 million row data set, for example, pclean has inferred the existence of about 1.1 million distinct physicians, around 400 medical schools, and around 15,000 cities. And this isn't always a super easy inference. For example, there are actually way more unique city-state pairs than 15,000 in this data set, but some of them have been inferred to be typos of others. And that wasn't just done in a vacuum, that was done based on all the other information that was available to make that decision. For example, all of these places that say Abingdon, MD were actually for the same address. Maybe it's actually one error that's been propagated 150 times instead of 150 separate errors. Things like that that allow it to actually resolve these uncertainties. And the algorithm that it's using to do that is sequential Monte Carlo. I'm animating it here. So on the left, you're seeing rows of the flat data table come in. And on the right, you're seeing the growing hypothesis of what the latent relational database looks like. And at every iteration of this algorithm, pclean is making a number of sort of rational judgment calls based on estimated radon-Nikodym derivatives about how best to explain the data in that ring. Can the new row be explained using existing entities in the latent database, or do I need to create new objects? And if so, what are their likely attributes? And periodically during this process, we also run Markov chain Monte Carlo moves to try and fix any short-sighted decisions that were made in light of new data that's come in since we made those decisions. So we're going to loop through our latent database, considering each object in turn. That's what you're seeing in yellow highlights here. And in blue, you're seeing all the data and other objects that are currently hypothesized to somehow be informative about that object that we're reconsidering right now. And in light of all that blue data, pClean is going to make another set of judgment calls. Would this data be better explained if the hospital had a different name, or we're in a different city, or we're actually the same hospital as a different hospital? Right? And the score that helps it decide whether to accept or reject one of those corrections is, again, one of these automated Radon-Nikodym derivatives. Once we've inferred this latent database, one nice use case is that we can actually go and reconstruct the flat table and look at what changed. And that's a way of cleaning the data. So in this physician's case, we saw that that about around 8,000 cells had changed after we did this. And Monica Agrawal, my co-author, and I got some pizza and went through these 8,000 corrections and tried to find on Google, could we verify that they were actually right? Because there's no ground truth data for this big Medicare data set. It is the ground truth to the extent that one exists. And so we went to Google and tried to look these up, and we were able to verify 96% of those. Now, because some data is duplicated, some of those 96% are kind of, it did a fix somewhere and it found out all the places to apply it, right? But still, that's pretty nice. Now, it also made 1.5 million imputations, things that were missing in the original table that we were able to fill in. And we did not go through all 1.5 million of those, but we looked at 100 of them, and we were able to find verifying information for 90 of those 100. Okay, so there's some other results, but just for time reasons, I'm going to spend the last 5 minutes talking about this other project, language model probabilistic programming. And this is about whether there's a more principled compositional way to control language models than just giving them prompts. So why would we want that? Well, when we ask a language model a question, like, tell me a joke, behind the scenes, the model is computing a probability distribution over all the possible answers it might give. There's infinitely many available responses, and the language model is assigning higher probability to some and lower probability to others. And every time we use ChatGPT, we're actually just getting a sample from this distribution. Now, the main way today that we get language models to do what we want is we prompt them, which changes the output distribution. So I can say, instead of a joke, tell me a joke about animals. And what we're hoping happens is that some of these jokes are downweighted and other ones are upweighted, so that when we sample, I am more likely to get a joke that's about animals. And because natural language is actually so expressive and compositional, I can use prompts to express all sorts of things that I want to do to this distribution. I can say, I want to ask for a joke that only uses really short words that are less than 5 letters long. And I should hope that that downweights most of the jokes and upweights the very few that satisfy the constraints, so I can hear about what you call a bear with no teeth, the gummy bear. And this is how we'd like things to work, but prompting can be an unreliable way to control the output distribution of language models. So for example, a few weeks ago, I asked the GPT-4o API to do these things. And I'm not sure that's the same as what ChatGPT is using. They might have a system prompt that's not active in the API. So this was surprisingly bad to me, but this is what happened. The distribution that I got from sampling a few times actually looks something like this. So sometimes it gives a good answer, but with surprisingly high probability, it actually starts to tell a joke that has nothing to do with animals. Like, why don't scientists trust atoms? Because they make up everything. And then it corrects itself. Oh, wait, that's not an animal joke. Right? And then it gives you an animal joke. Okay. When I asked, and another thing that's interesting here is that there actually, if you didn't ask it for a joke about animals, there were some jokes that it gave about animals, like the gummy bear joke, right? Why isn't it giving me those? And somehow we haven't done what we thought we were doing to the distribution of just upweighting the things that were already there that are about animals and downweighting the things that aren't. When I asked it to tell me a joke with only short words, it did give me something with only short words, but it was, why did the cat sit on the mat? It saw a hat, which is either not a joke or just a very bad joke, but either way, this is clearly an imperfect way to compositionally shape the output distribution that we want the system to give, because that teeth joke actually would have satisfied the constraint. So what we tried to do in this project, called language model probabilistic programming, is develop 2 toolkits for controlling language models more effectively. Okay? First, we have tools for modeling. These are new ways beyond just prompting for specifying the target distribution that we actually want to generate samples from. And second, we have tools for inference, algorithms for drawing good samples from that target distribution, because like a lot of the things we've seen in this talk, actually getting those target distribution samples is generally going to be intractable. So on the modeling side, what does that look like? Well, the toolkit is going to let us take a distribution of a language model on some prompt and programmatically modify it. So for example, we can say that we want to remove everything that's not runnable Python from this distribution, yielding a new distribution that would be intractable to generate from naively, because it would require sort of like one way to sample from this distribution would just be to sample over and over again until we got something that satisfied the constraint, right? We don't want to do that, but at least this is a nice distribution that if we could sample from it, we'd be guaranteed to get valid Python out, right? As another more whimsical example, here's an interesting task proposed by Bubek et al. As an example where today's language models really struggle. The goal is to come up with a first line of a poem that if you read the words backward could be the last line of the poem, okay? Now, if you ask GPT-4 to do this, it's going to say something. It says something like dawn silence whispers softly, evening's echoes fades, which maybe sounds kind of poetic, but if you try to read it backward, you get fades, echo, evenings, softly whispers, silence dawns, which is not syntactic English, right? Here's what we can do with language model probabilistic programming. We can say, start with the two distributions. The poem begins with the words and the poem ends with the words, right? There's some stuff that the language model will want to say for each of these prompts, two totally separate distributions. Then we're going to push the second distribution forward through the reverse function, which means that we're going to take every string in it and without changing the probability of the string, reverse the words, okay? So now we get a distribution over reversed ends of poems. And then we're going to take the intersection of these two distributions by taking their pointwise product, which is going to leave only the high probability answers that are good under both distributions. And I don't know what the true target distribution looks like here, because it's actually quite a hard task even for people to do to answer this question. But when we used our system to sample it, we got things like, there was nothing but love in her eyes, which if you reverse it, gives eyes her in love, but nothing was there, right? It's not bad. Now, the algorithm that we actually use to draw those samples is, again, a sequential Monte Carlo algorithm. Like the one we saw in the last example, it's doing something sequential, except instead of building up a database, it's building up strings. So we have processes that are kind of trying out different words, and this is for a slightly different problem than the one I just talked about. I'm sorry about that. But periodically during generation, we're going to ask which of these particles are good. And the way we're going to do that is by estimating these radon-Nikodym derivatives between the actual target distribution that the user says they want to sample from and the thing that we're actually doing, which is just an approximation to that. And the ones that are particularly get a low score in that metric, we're not going to let continue. And we're going to use the computation instead to focus on the ones that seem to be doing a better job already. And then we're going to keep going. And so every few tokens, we're going to do another of these radon-Nikodym derivative reweighting steps and start again. And the nice thing about this algorithm is that as you increase n, the number of parallel particles that's sort of your computation budget, you actually do converge to the target distribution that the user has specified using our modeling tools. So we've applied this. My collaborators especially have done a lot of the implementation work. So João, Ben Lebrun, and a whole team that I'll get to at the end of the talk, to boost language model performance on a variety of tasks, from Python coding to molecular synthesis. And it's often the case that a small language model plus a sequential Monte Carlo algorithm can beat a much larger language model without them. These methods still required us to manually write a language model probabilistic program in each domain, but Gabe Grant has been exploring whether language models themselves can write these language model probabilistic programs. So in Gabe's work, if we were to ask, tell me a joke about animals, the language model, instead of just trying to give me a joke, would actually say, okay, what they're asking me to do is tell a joke, but it's about animals. And that would then become a spec that we could actually run in our sequential Monte Carlo algorithm and get good answers. And Gabe has shown that on some constrained generation benchmarks, this architecture leads to really significant gains in the rate at which language models actually solve the task they're being assigned. So hopefully these two projects together start to give a picture of what I have in mind when I say that maybe these probabilistic generalizations of AD can open up new ways of building more auditable, more controllable, more intelligent probabilistic software. Thank you.